Hey Jesse, how you doing here? It is time for office hours. Get started on some questions if you want. Bet chapter 6. I need to look at and see who did chapter 5. Doing well, doing well. Make sure all my lights are on. It is Thursday morning. Oh my gosh. Let's see. I need to go and unfortunately put in. Let me get the notes up for the lecture, or for this, not the lecture, but for the office hours. Did I save this? I saved that. That should be saved. That is from yesterday's class. Okay. Let's go check this out right here. Go ahead and go to... Can we do some more review like we did in class? Sure. What chapters do you want to review? What chapters do you want to review? And we can do that. I'm going to go and enter in the zeros on my Pearson. No. Hey, all the zeros. It's a bummer. Got to enter in if people missed the assignments. And last night was a tough one. I think last night, chapter 5, part 2 was due. And so I have to put in the manage incompletes. So go to that. What chapters would you like to do? What people struggle the most with on the test? Oh, well, that's a lot of chapter 5. Chapter 5 is usually the toughest for people. Well, pretty good. We only had about 2-3% not attempt the assignment. Oh, didn't do... Okay. There we go. Submit. Okay, we put in the zeros there. Now we go to the other class. Afternoon class, less students. I've had more students not do work in afternoon class. What percent didn't do work in the afternoon class? No, I hate putting in the zeros, but gotta do it. Sometimes we've had instructors not do it till the end of the semester, and that's a problem because then all of a sudden your grade drops. There we go. There we go. Shall I pass due? Okay. A little bit more in the afternoon, about 7% in the afternoon. No. Let me look at the grade book, and then we'll get started with some example problems here. How are the grades on that? Let me get an example problem up and going over here. Actually, not that bad. That's not bad. The average on chapter 5, part 2 was higher than part 1 quiz. That's weird. Well, I guess people had more time. Maybe they were like, okay, I got to get this down. Very impressed. Let's just throw 100 points because, wow. Afternoon class got an 86 median and a 75 mean, but the mean's going to get pulled down, but half the class got about a B average. It's very good right there. We like seeing that. So yeah, well, that's good news. My hair is crazy today. Crazy hair. Okay, let's go here and look at some chapter or some test questions. Okay, so let's think about what the test might look like. Let me write it down right here. Okay. Chapter Stat 201, Chapter 5 review. So what does Chapter 5 cover, Jesse? What is in Chapter 5? And we could pull up the review, and we could make a question from each review topic, which that's when you really know it, is you're like, okay, let me come up with a question from each review topic. I would say this is the best way to do it. And let's go here to the topics on the exam. Going on to Chapter 5. There's chapter 5 right here. And yep. Hey, Nick, what's up? Feel free to ask what you want. We're about to come up with a review question based on each of these things right here from chapter 5. Okay. So you have to be like, what could we possibly ask from each of these? First thing is calculate the z-score to compare two values. Well, why do we even use z-scores? Like if I tell you something costs 10 cents more, why would we even use z-scores? Because it's 10 cents a lot. Is 10 cents a lot? Something costs 10 cents more. Is that a lot? It's 10 cents. It's not? It depends. You might be like, 10 cents? Come on. But it depends on what it is. Trunk's got it right there. Depends on the context, right? When I was growing up, there was penny candy, like little Tootsie Rolls. Hey, Trunk, howdy. Good to see you here. So if penny candy costs 10 cents more, it's 11 cents candy. If nails that you use to build a house cost 10 cents more, they're probably costing like 11 cents. Like you can get a box of nails for like $3 or $4, I think. I don't know. I don't buy nails that often. But every time I buy a box of nails, I get like 200 nails. And it's like 200 nails for $5. So you're getting like each nail for like 2-3 cents. And then if the price of nails goes up by 10 cents, well, that would dramatically impact everything created by nails, such as we see with the price of eggs. Like, is an increase in the price of something by $2 a lot? Well, for eggs that have gone up like $2-3, that's a big increase because it's almost like a 100% increase. When you compare it to kind of the average price of eggs over time, all of a sudden now it's a lot more. But let's say cars go up by $2 or $3. Well, if the price of a car goes up by $2 or $3, you're not even going to notice it. Now and laters are 25 cents. What, for a now and later? No, like a pack of now and laters is 25 cents, right? Like, not like a now and later, right? Like just the one, right? Not a, no, a pack. Okay, good. Yeah, I was about to say, if one single now and later is 25 cents, I'm going to feel super old. Back in the day, yeah, they were probably like 5 cents. I don't think that was the penny candy, like a single now and later. But there was a bookstore that I would go to. Really nice old lady ran it, and she had penny candy, and you could just get like Tootsie Rolls and little like bubblegum things for like pennies. She just had these bins up the front, and you would just hand her like 10 pieces of candy, and you'd give her a dime. Man, that makes me sound old. She probably wasn't making much money off of that anyways. But to think that she could get all that candy, I don't know. She might have been losing money on it. Maybe she just liked to do that for the kids. Oh, I bet she did. I loved it. Walk down there and get some penny candy. But anyways, as you can tell, the context matters, and that's why we use z-scores. So that's the first concept right there, is using z-scores. Oh, the McChicken's $2 now? Yeah, so I mean, McChicken going up by $1 off the dollar menu. A McDouble used to be like, Little Caesars is now $6.29, $5 hot and ready. No longer $5 hot and ready. $5 footlongs probably don't exist. Used to be $5 February. They'd be like $5 footlongs. See, they got a jingle that puts in your head. Pizza, pizza. All the stuff we know. I'm loving it. Let's get going here. Calculate a z-score. And to calculate a z-score, what is the equation? So you should memorize the equation because it is what a z-score is. Because if I were to tell you some information, like if I were to say you made a 70 on a test, you tell your parents they should be proud of you. Would you ever tell your parents, they should be proud if you made a 70? Let's think of some context to this where you made a 70 on a test, and you would tell your parents, yes, there's context to this, right? Your parents like, you made a 7, you're like, listen. This was an organic chem test. And these tests are insane. Like, notoriously, people fail them. People get zeros on these tests. So the average was a 40, and the standard deviation was a 10. So if you know z-scores, exactly. So Jesse's seeing where I'm going with this. Can you do the z-score like this? Like, if you know how to do z-scores, you can, boom, Jesse just did it instantaneously, and let's write down the equation. So this is where we know what a z-score is, and we know how to calculate it based on the observation, which is y. That's the observed value, what we scored. Like, I observed someone scoring a 70 on the test. Like, I see that. That's the value observed. The average, which is the mean. I like to use the mu for the mean. Great job, Jesse, right there, writing the notation in the chat. And then we have here the standard deviation. The other possible notation is to use the sample notation, which would be y bar. That stands for sample mean right there, and also s. I prefer not to use those, but the equation would look like y minus y bar, the observation minus the mean, over the standard deviation equals z-score. It's just a difference in notation where I use the observation minus the population mean over the standard deviation. Both of them mean the same thing. The top part of this equation is just a difference. How far is the observation from the mean? And then in terms of standard deviations, which gives us what the z-score is. A z-score is how many standard deviations something is above or below the mean. And it's very important whenever we compare things to each other, we actually plot the z-score, because the z-score is going to give us context to how many standard deviations something is above or below the mean. So you'll always see me adding z-scores to this. Like, here's the actual scores on the test, like an 85, 75. This is a different problem. But the z-score here of 0 tells us that the mean of the test was 75, because at the z-score of 0, we're right on it. And then you can tell the standard deviation is 10, because that's how many units we're going up here. This curve right here is called the what normal curve. That curve, I'll try to find a better version that I've drawn of it lately, but that curve right there is called the what normal curve. So when I put the z-scores on this curve, it is called the what normal curve. which I do for every problem. So I could write this problem right here and do like this. This is called the standard normal curve. So that's the standard normal curve right there with z-scores on it. And then we can use the empirical rule. Let's see what it asks next for us to understand. But z-scores, great job, Trung and Jesse right there, the standard normal curve. So the 68, 95, 99.7 rule, what the heck does that even mean? We're going to do all of chapter 5, then we'll do, I think, did Nick have a question? Someone else had a question. We'll do it next right here. What does the 68, 95, 99.7 rule mean? So we're doing each one of these right here and just talking over it. Check out the speedrun video for another version of this. But what does this even mean? Like, what's the point of the 68, 95? Like, you had to explain to someone what that means, because it's like, here's what you should know, the 68, 95, 99.7 rule. Well, we're going to probably tell you those numbers on the test, but what do they even mean? What do those numbers even mean to us? What's the point of those numbers? Why do we have 68, 95, 99.7? Correct. Great job right there. We can use them for percentiles, but Jesse said it perfectly right there that 68% of observations are expected to fall within plus or minus 1 standard deviation, and it's related to z-scores on the normal curve. So when you take the normal curve, each number works the same way, that if you draw the normal curve and then you go plus or minus 1 standard deviation, then you would expect 68% of observations to fall within here. Now use our previous problem. When it comes to the test that we just looked at, what does it mean for the previous problem right here? When it comes to the previous problem, we would expect what for the test grades? When it comes to the previous problem, we would expect what for the test grades? We would expect... Oh, Olivia right there. Good question. Is that 320, Olivia? Little 320. Should we do some 320 after? We could do some 320 interpret slope. Yeah, let me write that down right here. 320 interpret slope and intercept. BS 320 interpret slope and intercept. Okay, we'll do that here in just a little bit. You got it. So with this right here, what does this mean for this problem? Well, what does the 68 rule tell us about this data? I haven't drawn it out yet, but what does 68 mean for this data in context? Like, what is the context of 68 right here? What does that mean? The context of 68 would mean what? We would expect to see, if normally distributed data is here, we'd expect 68% of people to get between a 30 and a 50. Exactly. So, whoops, got the highlighter still on. That's exactly it right there, Jesse, and that's what this rule means. And we can use it for a lot of information, because what if I asked you right here the probability of people getting a 50 or higher? So that's where we might use the rule to say, what is the probability of people getting a 50 or higher on this test, given the data is normally distributed? I think you'll be able to solve that pretty quickly, Jesse. Yep. And so this is the utilization of the rule using the z-scores, and great job, Trung, right there. So we should be able to solve things like this. If you're wondering how we got it, it's because if 68's inside, 32 is total outside, and half of 32 is 16, leaving 16% on either side right there. And so we're just trying to figure out the percents under the curve, and we did a lot of problems doing this. Check out the practice test for a lot of great examples. Let's do a little more right here, and then I think we'll do the slope and intercept, which is on test 2 for 201. So if you're in 201, test 2 will be a good test to cover what we just cover, what we'll cover here in a moment. Understand z-scores, standard deviations as a ruler. Well, that means that z-scores are going to standardize the data. So we've already kind of talked about that right here. Interpret normal probability plots and goodness of fit test. Well, what's really great right here, Olivia, is this is also a 320 crossover to interpreting a normal probability plot and a goodness of fit test. So when we do a normal probability plot, I actually made really good graphics over here on the Discord. Where is it? BAS 320. I'm going to go grab the picture. And Olivia, feel free to join the BAS 320 Discord. We're talking a lot of great stuff in there and interpretations. So here is, let me take a screenshot of the picture. And we need to zoom in on this a little bit. There we go. Okay, so here are 3 normal probability plots for 3 different flowers. Actually, I could make the code for it again. So I did post the code. Okay, let's post the code again. Okay, here we go. Does the code work? There we go. I should have just done that. Here are 3 separate normal probability plots. Which of these is the least normal? You can just say red, blue, green, whatever you want. Which of these is the least normal? Here are 3 normal probability plots. Which of these is the least normal? Jesse, you're 100% right. It's the blue, and it's due to this area right here. None of them are really bad. The more it follows the line down the center, the more normal it is. You're not really saying that there's a linear relationship here. You're saying that the sample lines up with the theoretical answers. And so you're seeing that the green lines up really well. And the little boundaries are kind of your like gimme zones, like, it's kind of okay. But the blue has some deviations on the high side. So that shows non-normality. Just to kind of review again, I'm going to use a QQ plot here. I'm going to go random normal. And we're going to do 1,000 observations. This is normal data. So if I make a normal probability plot of it, it follows the red line down the center. And then if you look at the histogram looks what? 2 concepts. If it's normal, it should look pretty what? If it's normal, it should look pretty what? That's a normal histogram, unimodal symmetric, exactly. And this is quantitative data because it's actual numbers. But this data here looks very, very right skewed. Remember, we like to review every concept we can. It's right skewed because right to the high, left to the low, whatever way the monster man's tail goes. My students never miss that question, I hope. I've seen 1 or 2 miss it, but sometimes there's a question that's like, this distribution is right skewed. And people are like, no, it's left skewed. And I'm like, no, it's right skewed. So now the QQ plot or the normal probability plot will not follow the straight line. Now, yesterday in class, it is stuck in my... I know, right? You can't get that one wrong. So a lot of the things we do early on, you'll be like right to the high, left to the low, whatever way the monster man's tail goes. This one, Jesse, is where people are going to start to get confused, though. This one is a goodness of fit test. And so this is something we covered a while ago. So a goodness of fit test works the following way. This is... You got to write this down because this is almost memorization. I can go into greater detail and make it better than memorization. We are going to fit a normal curve on this. High p-value, it's normal, like it's a good fit. Low p-value, not normal, it's a bad fit. Okay. So what are we using to make our decision on if it's normal or not normal right here? And this is where people say, but isn't that for correlation? P-values are used everywhere in statistics. I mean, not everywhere, but like a lot. We're going to use the p-value, and that's going to be the key concept. And when we say low p-value, what do we mean by low p-value? Someone might be watching this in the future and be like, wait, what do you mean by low p-value? A low p-value is any p-value that is what? A low p-value is a p-value what? Which means unlikely by random chance. Less than 0.05. Statistically significant, unlikely by random chance. So those are low p-values. So I'll give a little more detail on this in a moment, but the memorization of this, which is probably one of the first ways we learn things, is to just memorize it, is to say here, if the p-value is low on the goodness of fit test, we have evidence it's not normal. If the p-value is high on the goodness of fit test, we would continue to believe it's normal. So even more simply, high p-value on this test, normal. Low p-value, not normal. Hey, Brian. Hey, what's up, Adam? Lovely day here in Nashville. Thank you, Adam, right there. And so good to see you always. Well, so think about this. Does that look like a good fit, Jesse? Do you think the p-value will be high or low when I run the test right here? So we have data. Here's what the histogram looks like. Here's the normal probability plot. It follows the line. Do you think the p-value will be high or low? So high means normal on this test, and low means not normal. Like, it's going to tell us what it thinks about this data. It's going to analyze it and say, it's going to be high. Yeah, exactly. Should be high. High p-value. Yep, exactly. So that means we would continue to believe it's normal. So I'm going to go a little more detail on this. So this is the advanced way to think about it. So if you're wondering, like, what does this actually mean? It's telling us the probability of seeing something like this given the data is normal. So what we assume at the start of this test is that this data is normal, and then we say, here's our observed result. So this data right here is a likely result given the data is normal. Does that make sense? Like, seeing something like this is probable given the data is normal. So think about the next way I could talk about it. Seeing something like this is what, and that is about like that right there. Now, one off. Seeing something like this over here is what given the data is normal. So seeing something like this over here is what given the data is normal. Is, well, not really probable, not likely. So it's not likely to see this. See, Trong, well, we have evidence it's not normal. And that's exactly it right there. Like, you can just look at this and say evidence not normal due to the goodness fit test. And so we would say we have evidence it's not normal. It can also be done over here and jump really quickly. If you go to analyze distribution, take your variable of interest, run it, go here to, it just takes a few more clicks, goodness of fit test or continuous fit normal. It's going to fit a normal on top of this data. That normal doesn't look to fit too well, but you'd be shocked with small sample sizes that over here, when we run the test on the goodness of fit, the p-value actually comes back high. It's good to see you, Trung. So be very careful, Jesse. So this data over here, would you conclude, and we use Shapiro-Wilk generally, would you conclude normal or not normal for this data? And just, if you go by the base knowledge, don't look at the data and be like, that doesn't, But would you conclude normal or not normal? Due to the goodness of fit test. Normal, exactly, yeah. And then you can just use the base knowledge of high p-value, low p-value. The reason this actually gets back into something we talked about yesterday, with a small sample size, it might be hard to find results. There's only 16 observations right here, and you're thinking, yeah, I don't know, that data could be normal. Like, I don't know. I mean, there's only 16 observations. Maybe it's normal. Like, the test is not giving, it says there's not enough evidence to say it's not normal. Like, that's a more deeper understanding to say, at this point, we do not have enough evidence to say that it's not normal. Evidence is low p-value. And this one, do we have a lot of evidence that this data is not normal? So look at the p-value over here. Do we have a lot of evidence for this one that it's not normal? And look at how small the p-value is. Do we have a lot of evidence that this is not normal? Yeah, we got tons of evidence. If you were to bring this down to 20 observations and you had data that looked like that, my guess is, you see, ooh, look at this. This is interesting. You see how right skewed that is? What do you conclude for this one with this test? Normal or not normal? Don't look at the right skew because that's going to trick you. So you would conclude what for that test right there? You'd conclude normal. In truth, it actually comes from a skewed, this is an exponential distribution of numbers. I only simulated 20 numbers, so due to the small sample size. So Jesse, that's hopefully, it is, well, so you could add that. You could be like, the p-value is a little bit low. It's not statistically significant though. That's the number one thing we care about is the p-value below 0.05. So that's like that's the cutoff for where we're like, no, that's too unlikely. So you could say the p-value came back of 0.192. That's a little low, but not low enough for us to include not normal. Does that make sense? We use the 0.05 standard unless we play with alpha. More on that later in the semester. But you would never put your alpha this high. Yeah. So, but the easiest way to memorize it for the goodness of fit test, high p-value, normal, low p-value, not normal. Let's do a little through 20, then we can come back to this. Jesse, what other questions do you want to do? But we've reviewed a little bit of chapter 5 right here. I mean, we're basically going step by step. Identifying outliers. Outliers can do anything. They're the ones that deviate from the plots. You should know outliers can do anything. Very, very big right there. Let's do some interpretations. So Jesse, hang out for this if you want. And if you were to lose points on the 201 for this, you could tell me, because this is the advanced interpretations we do in 320. So I'm about to do advanced interpretations for 320. Amen, good to see you here. What are you studying, Amen, right now? We're going to make Amen a mod. They're here from another place, I think. So good to see you. Let us know what topics you want to talk about. They might converge, and if they converge with what we're studying, Amen, well, you got it. And am I pronouncing your name correct, Amen? Is it Amen or Amen? I'm very bad at pronouncing things, but if you want, tell me how to pronounce your name and I will get it right. Okay, let's head over to the main screen. Let's do it. Okay, so we're going to do some slope and intercept. Class, well, enjoy your class here in a little bit. We're going to do slope and intercept, which is regression, chapter 7 in 201. And this is the main crux of 320, is all about regression. So to do regression, we need what kind of variables? I'll show you. I'm going to start doing a regression in the background. So you're going to see me do a regression right here. I'm loading up some data. What kind of variables do we need for regression? And here's where I'm making my model. This says model save into, that's M for model. I'm just storing into the object M. And then I'm going to do height, hint, weight, and then data equals survey 10. Okay, so that right there is the linear model. So this stands for LM, linear model. We're using height and weight, and what kind of variables are those? So what kind of variables are height and weight? That's the key. What kind of variables are height and weight? And you've got a hint right over here. What kind of variables are height and weight? It says num. What do you think num means? We don't usually call things numbers into quantitative. You got it right there, quantitative. So regression takes two quantitative variables. We'll have some tricks for that later on in 320. So let's think about bad interpretations to start. We're going to visualize the model right here, and we're going to see how weight explains height. Would you say, and this is the very simple explanation, I have an exam on the 27th. Yeah, well, tell me the concepts you want to do, and I'll make up some practice problems for you, Amen, right there. Just be like, we're covering the normal model, we're covering this or that. Yeah. Oh, thank you so much, Amen, right there. Just say like normal model, correlation, and I'll come up with concepts. Your class might be taught differently, so always ask your instructor, like, how should I do it? It's a final exam. Tell me the concepts it's covering. T-test. Maybe we'll do a T-test or something. T-test, chi-squared, ANOVA, who knows what you're covering. But let us know, and I might be able to do some. Thank you, Amen. Okay, so this is our model. People who weigh more are generally taller. Now, that's not a full interpretation of the coefficient, but we can just see it visually that the red line here is the linear model. This is the prediction interval, this is the confidence interval for the mean. This is the prediction interval for individuals. I'm not going to really interpret those right now, but they're decent to know. These are the individuals. Like this person right here is 75 inches tall and weighs 75 pounds. I think they made an error. They're a big outlier here, so that's a problem. Let's make a summary of our model. Now, when you get the summary right here, where are the coefficients? So where's the intercept and where's the slope? Oh, are you doing Pearson? Do you do Pearson, Amen? Oh, cool. Okay. Yeah, you're like same book. Okay. Well, then just hang around. And you could also check out the review 1 page. It has, and then you'll see the Stat 1 website right here. Mubot's about to post all these links for you. So that's all the review pages, and that has like the slope is exactly. And so that's just what the slope is. And the way to read this is to kind of crosshair in on the things you're looking for. So you'd be like, okay, the estimate of weight, which is the x variable, is this right here. That's the coefficient of the slope. So that's the coefficient of the slope. And then the estimate of the intercept is this one right here. Now you might wonder what the other things are. You're welcome, Amen. Yep, we'll do some practice problems because we got test 1 coming up and you cover that material. So the standard errors are your uncertainty in those estimates. Have you ever told someone, I'll be to your house at 5 p.m.? You have a friend, you're like, hey, I'll be there at 5 p.m. And then you show up at 5:01. They're like, you said you'd be here at 5 p.m. And I said, well, I'll be here at 5 p.m., but I don't know, within 5 minutes. So the next time you show up at 5:06. And they say, but you said you'd be here at 5 p.m., but within 5 minutes. And you're like, well, that's just an estimate of my uncertainty. So we think the slope is 0.073249, right? But we have an uncertainty in that estimate. Just like we think we will show up at 5 p.m., but we could be off by about 5 minutes. Now, that doesn't mean we will be off by 5 minutes. Does that make sense, Olivia, to talk about this way? It's like, we think we will be there at 5 p.m. That's our estimate of when we will show up. Like, oh, I'll be there about 5 p.m. And then your friend's like, wait, but you won't be there exactly. And you're like, well, I don't know, within 5 minutes. And that doesn't mean we will be there within exactly 5 minutes. It's like, I don't know, maybe sometimes 2 minutes, maybe sometimes 6 minutes, probably not like 20 minutes, right? Like imagine if you told someone you'll be there within 5 minutes of 5 p.m. and then you show up an hour later. Well, they'd be like, your uncertainty on your estimate was off. So every estimate has a certain amount of uncertainty in it. And what's really, really cool, and I want to show this, is I can actually make for you a 95% confidence interval with this, because then I hope, is Jesse, are you still here? So Jesse, if this is the standard deviation, basically, it's called a standard error because it's based on a sample. How do you think I could be 95% confident around the estimate? Ah, Jesse, thank you so much. What would I do? What number springs into your mind if I wanted to be 95% confident and maybe go around that estimate. I would go what around it. And this relates to your class too, Jesse. This is and so I'm in too. If I wanted to be 95% confident around that estimate, I would probably go what around it. 95% confident. What do you think I would do? And then we're going to interpret the coefficients here in a moment. If I want to be 95%, well, so think about this. When we go 95% out on the curve, where do we go? When we go 95% out on the curve, where do we go? We go plus or minus what? When we go 95 out on the curve, we go plus or minus what? 2 z-scores, right? So watch this. 2 z-scores is basically 0.6, right? So times that by 2, it's that. So what if I go here and add to this 1.2 and subtract from it 1.2? Now I can run the code to do it, so I don't have to do it by hand, and look at these answers. So here's the lower answer. The lower answer I got was this, and the upper answer I got was this. Are those answers right down there that I calculated pretty close to the actual answers? So the lower answers are the ones I calculated. Great job, Almond, right there. So think about that. I just said, well, let's go plus or minus 2 z-scores. Now, the technicality of it is this does use t's, but the computer software does it for us. We use a lot of software, Almond, so we don't, hopefully that, definitely talk to your teacher and be like, how is our test going to look? Because we use a lot of software in our classes to get answers, because that's what modern technology does for us. And so I was able to basically calculate it in my head by just saying, well, it's basically plus or minus 2 standard deviations on the curve. And basically, it's more like 1.96. So if I had done the 1.96 and carried decimals, I'd have gotten the right answers by hand. But why do it by hand when the software does it for us? So this right here, this t value is a ratio. And so we'll just talk about this real briefly, and then we'll interpret all this. The t value is a ratio of your estimate to your uncertainty. Do you notice the ratio right here is about 100? Because think about this. Our estimate is about 100 times bigger than our uncertainty in it. Would you imagine I say to you, the price of a car costs $20,000, but I could be off by about $1. You would tell me I have very little or very much uncertainty in the car. If I tell you the price of a car is about $20,000, but I could be off by about $1, does it sound like my uncertainty is high or low? If I say, that car's about $20,000, but I could be off by about $1, would that be a lot of uncertainty or a little bit of uncertainty? It'd be very low uncertainty. But if I said penny candy, which we talked about first, costs about a penny, but I could be off by about $1, well, now you have pretty much all uncertainty in the price of penny candy, right? So if the penny candy estimate is a penny and then the uncertainty is $1, well, then you've got ridiculous amounts of uncertainty. So what do you think we want our t ratio to be? We want it to be very large. The sign of it doesn't matter, because the more extreme the t ratio is going to be what's important, because we're going to look at the absolute value of the t. So we see p-values here once again, and what the p-value is testing for is to see if these values are equal to 0. So when the p-value is low, we have evidence that these are not equal to 0. So what we are looking for here is that weight is significant in explaining height. Does weight have a significant relationship in explaining height? The intercept is not so important. The intercept's not equal to 0. Cool. Or we have evidence the intercept is not equal to 0. But the low p-value here in this shows us evidence that weight has a significant relationship with height. That means I bet your p-value, don't tell me your p-value yet, I bet your p-value is something like this. Is that close to what your p-value is? Maybe not exactly, because that would mean if we draw the curve, you landed over here at a t-score about here at t equals negative 0.04. Oh, it's gonna be even higher, Olivia. It's gonna be something like that, right? Your p-value over here on this side, your p-value is super high, because you're gonna be, if you were to draw the curve, it's basically the whole curve. So that is a very small t ratio. That means your estimate was probably close to 0. Your t value, which I'm going to put numbers next to these. I want you to tell me which number You're telling me a certain number is negative 0.392. Here's number 1, 2, 3, 4. Which one are you telling me, Olivia? Is that negative 0. Number 5? And then what is number 7? Number 7 in your output is what? What is number 7 in your output? Yes. Okay, good. So that is saying that the intercept is not statistically significant. What is value 6 in your output? Because if you're telling me the value 6, I think is your slope. That's your slope t-value, and that one's going to be bigger. Value 6 in your... Yeah, and then the p-value over here is the tiny one, right? So value 6 is a very large t statistic, and then your p-value on your slope is very, very tiny. So your intercept, which doesn't matter, is not statistically significant for you. That doesn't matter. The intercept is just a point, but the slope of the model, which is the lower one, is the one we actually care about because the slope is the XY relationship. Does that make sense? We care if the slope is statistically significant. Here's a model with an intercept not equal to 0. Here's a model with a slope not equal to 0. Which of these models, A or B, looks more like X and Y have a relationship? So this is where the intercept, B0, is not equal to 0. This is where the slope, B1, is not equal to 0. Which of those models look like X, Y have a relationship? Model B. So we don't care if the intercept is not equal to 0 because that's just an arbitrary point over here. The line could still be flat. We care about the slope not being equal to 0 because that's the XY relationship. And so this is the significance we care about, and it's based on the estimate of the slope over here. Does that make more sense, Olivia? So that's why we care about the significance of the slope, because the slope is the XY relationship. The intercept is just an arbitrary point at where maybe it's not 0. Cool, the intercept's not 0. Well, is there an XY relationship? So now let's get to interpreting what this means. The absolute worst interpretation ever is the following. When someone... don't write this one down. I should be like... Don't write this down. When someone increases their weight by 1 pound, their height will increase by 0.07 inches. What's wrong with that? So 201 should also kind of know, and Jesse, feel free to leave at any moment, but I'm always like wanting you to hear like what's wrong with this interpretation. When someone increases their weight by 1 pound, their height will increase by 0.07. Well, there's no on average. We like that a lot of times, but we use words like will, and it makes it sound like cause and effect. Because think about the interpretation. When someone increases their weight by 1 pound, their height will increase by 0.073 inches. What would happen if Brian gained 100 pounds? What I'm saying is, when someone increases their weight by 100 pounds, you could move the decimals, their height will increase by this. Do you want to be taller? According to what we're saying right here, if you want to be taller, just do what? Think about what this says. Hey, Sloan, good to see you here. Think about what this says. If you want to be taller, just do what? What are we telling people with this? It says when someone increases their weight by 100 pounds, so we times this by 100 to find out what 100 units of the slope coefficient is. So when someone increases their weight by 100 pounds, their height will increase by 7.3 inches. What is that telling people? If you want to be taller, just do what? Is this the way the world works? Just gain weight. You want to be in the NBA? Just go eat cheeseburgers. Don't do that. But here's the thing. Let's take two people. Let's take a person A and a person B. And we can actually see these people over here in the model. So, or we'll use 150, 250 because I can go right to those lines. Okay. On your way to McDonald's. I don't know if you're serious or not. NBA, I like Slow 100 points. That's like, that's the best jokes right there. Okay. So if we were to take two people, and this is the right interpretation we're doing now, two people in this model, where one person What does this person right here weigh? This person right here weighs 150. Does that make sense? Their weight, that circle right there is 150. This person over here weighs, and we're just rounding them, about 250. We're just going to round them to 250. So there's two people. Does that make sense? Two people. How much would you, they differ by, we'll say they're at 150 there and 250. We're just going to round them to that. How much would you expect their height to differ by? Do you have any strong estimates on the differences you would expect between these two people's heights? Now, they have a true difference. There is a truth to the difference in their heights, but what would you expect their difference to be? They differ by 100 pounds. So they differ by 100 pounds. You would expect their heights to differ by what? That's it, Olivia, and we just did the interpretation, but we didn't write it out fully. So here's the interpretation. Two people, and that's the context. You don't always say two people. You got to talk about what the context is. Two people who differ in their weight by 1 pound are expected to differ in their height by 0.073 inches, where the person who is taller, who weighs more is expected, you could say on average, where the person who weighs more is expected to be taller. There we go. So think about it. Two people. Let's bring back up our graphic. We've got two people over here. Two people who differ in their weight by 1 pound. So now we're talking about people very close to each other. Just a little tiny difference right there. So if you had a person who weighed 150 and 151, we're just talking a 1 unit difference, 150 and 151. Two people who differ by their weight in 1 pound are expected to differ in their height by 0.073 inches on average, where the person who weighs more, this person over here, is expected to be taller. Now, not words, and keywords here, do not say things like, do not say this, because there are a lot of people who do not fit this mold. As in, we have two people right here who differ by 100 units. Here's a person who weighs 150 right here, and here's a person who weighs 250 over here, and they're expected to be differing by about this. But if you look over here at the scale, they differ by about -7. So we expected the person who weighed more to be taller, but the person who weighed more actually was very much shorter. So we always want to talk about expected differences. That is key. It's all about expected differences. So don't say words like will right there. We can do one more example right here, and we could do the intercept. The intercept's going to be illogical right here. If you think about mathematically, the intercept is when x is equal to what? And that's a good way to interpret it. So where is the intercept, Olivia? Where is the intercept? On this graphic, the y-intercept, the y-intercept is where? And we could probably go plot it. Let me make a plot right here while you think that over. So plot, I think it's x comma y. No. Oh, because we're using that. That is where the intercept is at. That is correct. And if you think about it visually, here, I'll visualize it. So survey. I think it's always good to see stuff. And that's good. Okay. And then we're going to go AB line M col equals red. And line width equals 2. Okay. And how do I change the axes on this one? And then plot, is it xlim? No, it's not going to do it. I don't know how to change the plot limits. Give me 2 seconds here, Olivia. I want to show it visually. Let me try this. GG scatter. Yes. Okay. We're going to go here to survey 10. We're going to do x equals weight. I should have used this to begin with because I've been using a lot of GG scatters. Y equals height. And there it is right there. And then add equals reg dot line. There we go. And we won't worry about the color of it. And now It's going to extend it. I wish it would. And then let's go here to save the graphic into P and library plotly. And now let's go to ggplotly of P. Okay, there we go. So the x-intercept, well, that's a bummer, would be all the way over here where it hits down here. And I was hoping it would show it, and truthfully the other graphic, the simpler one, might have showed it if I could extend out the line. It just goes through the data. Darn, going through only the data. But the y-intercept, excuse me, is down here. So what does that mean? If the y-intercept, and I'll just continue the drawing, the y-intercept is down here, and you set at 56.34. What does that mean? Like, just think a little bit what that means. You don't have to be so exact, because my drawing's not even so exact, but what does that mean? Actually, be closer to about... What does this value mean? What does that value tell us? So try to interpret it. Don't worry about giving a perfect interpretation. Just think about what it means. That's better. Just look at this right here and look at this right here. What does the line make for us? The line makes what? Now, in notation, the line gives values of y hat. Well, so that says has. Good guess there, Olivia. Good guess. So the line makes what value? Think of a P word right here. So the black dots, we would say, are the actual values. So that's an actual individual. Like this person here weighs about 270 and their height is about 5 feet. So they're about 60 inches tall. So they've got the following values. That's the actual for the individual. But the line makes what's is. The line starts with a P. The line makes what? Starts with a P. It's a line that would what somebody's height. I always like for people to think of the word and it's like, okay, then you might remember it when you're doing the test. Predictions. The line makes predictions, right? So this is the what's is for somebody who is, if we had somebody who was what? So think about interpreting. Olivia, this is good for you. This is test 201. And so if you understand it conceptually, the value of the y-intercept is the what for somebody who is what a what. So if we had someone down here, theoretically, this value right here would be their what. And then they would have a what. And then let's think about, does that make sense? That is the predicted height of somebody who is... I'm trying to say, I'm not trying not to say it. I want you to figure it out. I want you to write it in the chat and then you'd be like, predicted, well, close. So the value of the intercept is the predicted height if we had someone who weighed 0 pounds. Does that make sense? Because that's where the line hits the y-axis. So the y-intercept is the predicted value of y for observations that have x equal to 0. Now, this is illogical. Why? Why is this y-intercept illogical? Then we're going to write it out. Why is this y-intercept illogical? You always have to think about it. You'd say, okay, our y-intercept is that we would predict somebody to be 56.34 inches tall on average when they weigh 0 pounds. Jesse said right there, you can't weigh 0 pounds, so this is illogical. Exactly. So, and that's in 201, we talk about like a logical intercept. Here we go. Like here, check out the 201 notes on this too, because we go over like the intercept and the interpretations right here of the intercept. We almost did it yesterday. I was just trying to give a small introduction yesterday to the intercept and what it means and interpreting the values and do they have some logical interpretation. So in this instance right here, the intercept would not have a logical interpretation. Does the intercept have a reasonable interpretation right here? This is the exact thing we're covering right here from 201. There is no reasonable interpretation, and the interpretation would be, so we'd write the predicted height of someone who weighs 0 pounds is 56.34 inches. This is illogical because someone can't weigh 0 pounds. And that'd be a perfect, or you could say on average. Like it's predicted. You can always throw a little on average on there. Does that make sense, Olivia, right there? To think about what it means that we have the predicted, because the line makes predictions. The black dots are the actuals. We will talk about residuals and 201s, which is how much the line misses by. So you can actually see, where's residuals on here? Where's residuals? There's residuals. A residual is how much we miss the prediction by, or how much we miss the actual point by. So it's the distance it is away from the line. Yeah. And so all these concepts right here are in 201 and in 320. So really good crossover between, you see the Y and Y hat notation, which is what I'm using over here. The Y is an individual, which is a black dot. So you would say this person's Y value is their actual height, and then they were predicted to be 75 inches tall. So what was that? What is this person's residual right here? Ooh, Olivia, good question for you right there. This person right here who is 60 inches tall and was predicted to be 75 inches tall, what is their residual? Perfect answer, negative 15, exactly. So residual takes into account positive or negative. So if you're below the line, you're negative, and if you're above the line, you're positive. So positive means you are higher than what you were predicted to be. So everyone over here in this region has a positive residual, and over here has a negative. What does it mean if your residual is 0? If your residual was equal to 0, what does that mean for you? Because residual is just the formula, actual minus predicted equals residual. You were predicted perfectly, exactly. So you're on the line. So we need to understand these concepts of what a residual means. It's how well were you predicted. So anything on the line here would have a 0 residual, and it's just actual minus predicted. I would say residual wrap. Residual equals actual minus predicted right there. So I like to call it the actual, or the observed value of an individual, which an observed is that. That's pretty much our highest residual. You know it's really easy? You want to find residuals in R? Oh, what was that from? There you go. There's all the residuals. You want to graph your residuals? Just take your residuals, sort into X, and then go histogram of residuals. You want to see if your residuals are normal. There you go. There's, ooh, look at that. Non-normality on residuals. But also, you can just run check regression, because Petrie made this code, and just run it on your model, and you can see the non-normality of the residuals. And actually, we have a normal probability plot over here, Jesse, again. And the normal probability plot shows evidence of non-normality on the residuals, especially on the low side. And then we have to know how to look at the model right here. Then we'll look at things like, does the plot thicken into a 1? Olivia, any other questions? That's why I love code, because all the answers can be done really quickly. Ooh, and look, we got p-values, low p-values. Problem with linearity, problem with equal spread, problem with normality. This model has problems, and we probably could have saw that if we saw that the line bends right there. So let's use a polynomial model. And there you go. There's polynomial models. How to interpret R squared in BAS terms too. Oh, let's do a little R squared. So we actually just did this in Jesse, but I think Jesse has class at 2:55, so she's probably logging off. Thank you so much, Jesse. If you're still here, 100 points, you probably will still get those. Okay, so R squared. We actually have some R squareds down there right now, but is that just R squared, Olivia? And so you're hearing, we'll make sure to focus in on the exact topic, but I'm also going to show you some new things that you will be covering in class. Is that just R squared down there? It does say R squared, but it doesn't just say R squared, right? That is called R squared adjusted. So that is R squared adjusted for the amount of variables in the model. That isn't R squared adjusted. So with this right here, let's get the actual R squared. Here's the R squared right here. The multiple R squared. We don't want to use the R squared adjusted, which you can see right here. We want to use the actual value of R squared. So when it comes to R squared, what does it mean? And we did a drawing yesterday. Pull up that one here. Where is it? So the R squared is the reduction in the amount of variation there is in Y explained by our model. So it's a more complicated concept, but think about this. This model, the flatline model, is called the what model, Olivia? Have you learned this yet? The flatline model, which is the mean of Y, is called the what model? You're welcome, Jesse. Great job. Then it's called the, and thank you, Jess, Olivia, right there. Great answers. It's called the naive model. The naive model is when we use the mean of Y. So think about that. That uses no X's. So the mean of Y uses no X's, and we call it the naive model, like the no knowledge, the no X's model. So with this, we have right here, if we look at how far this is away, you would say this is a what from the model. Let's say this is +3, and let's say this is -3. You would say these are the what's from the model. Those distances right there could be known as the what's from that flat line. And we'll just look at the flat line only. So those distances right there would be the what's from the flat line, the residuals. Now, the problem with this is that if you have some are positive and some are negative, and you put the flat line, then what would you get if you add up all the positive and negative numbers? So think about if you have like this is +4, and this is -4, and this is -1, and this is +1, you'll get 0. So what could we do to numbers to make them all positive? What could we do to numbers to make them all positive? I'll show you visually. To make all the numbers positive, we could what the numbers. And this is the visualization of doing that. To make them all positive, we could simply what every number. We could actually, that is called mean absolute error. There is a way of doing that. That is mean. So you could absolute value them, but what did I do to them instead? So I'm not taking, that is a right answer. We got 3 points for that. You could do absolute value and you could find mean absolute error. There are ways of doing that. That is a valid statistical technique. But instead of doing that, I did what to the values? I turned them into what's. Like now, this is no longer 4, this is 16, this is 9, this is 1, this is 1, this is 9, this is 16. I squared them, right? Because if you square a negative, it becomes positive. And then I could take all those values and find the total error. And I could say 9, that's 26. So the total error is 52. What did I just do? And this is color-coded. So that's 52 if I add up all the values. I just think of a 3-letter word starts with an S. I just did what to these values? I just did what to those values? Think of a 3-letter word starts with an S. I found the sum of them, right? So maybe, what do you think SSE stands for? The what of the what? What do you think SSE stands for? Like, what did I just find? That value 52 is what? And then you'll know what SSE stands for, and I just mathematically did it right there. The error, because the residual is the error, the sum of the squared error. Great answers right there, Olivia. Does that make sense? It's the sum of the squared error. So that value 52 is the sum of the squared error from the model. And so it's 52 down below also, but we'll just leave that right there. But now I want you to look at the blue model right here. The blue model goes through all the points, right? How much error does the blue model have? It goes through all the points. That's the hint. So the blue model goes through all the points. How much error does the blue model have? If we were to find the sum of the squared error for the blue model, it would have 0 error. So guess what you've just found right here? You now have 52 minus 0 over 52. And you found r squared. Because r squared is the percent of variation in y, because the naive model gives the variation. Like, what is the variation around the mean? Does that make sense? Like, this is the variation around the mean of y, which is just variation in y. And then our model explains all the variation because our model has no error. Our model leaves nothing unexplained. So r squared here is equal to 1. Does that make sense? R squared is equal to 1 here. Now you could do a counterexample where you have data that looks like the following. And these are the deeper understandings. So here's your data. And here's the naive model, which is a flat line mean of y. And then here is our model. What do you notice about our model and the naive model, which we'll call this M for our model? What do you notice about our model and the naive model? They look what here? Our model and the naive model look what? Like if I were to start graphing mathematically the squared errors, like if I were to do it, there's the squared error from our model, and here's the squared error from the, whoops, not that big. There's the squared error from the naive model. Now, our model has a lot of error, right? So if we were to, and this is just a theory thing right now, if we were to look at the error from the naive model, it might be something like 110 or older 150. And then our model might have 149 error. And then we do that over the total error that existed. And then what would R squared be? What would R squared be? Like mathematically find what R squared is. And then we're going to interpret it. But this is the theory behind R squared right now. What would R squared be? I think so, right? Great job solving it. I think that's less than 1%, right? It's basically nothing. So 0.6% of the variation in Y is explained by our model. So our model really does a bad job right here, right? Our model explains nothing. So do ask your instructor how they want to interpret it. There's a few ways. Petrie mentions a few ways in his book, like knowing X gets you blank percent the way to understanding the variation in Y. Or I like to say blank percent of the variation in Y is explained. So these are two ways to do it right here. So if your R squared right here is 36, you want to times it by 100. So how would you interpret either one of these, Olivia, right here to talk about this? And you want to put in the X and Y. Here, I'll go back to the visualized model so we can see just the original model right there. But you want to put in your X and Y. So how would you do either one of these interpretations right here? How would you do either one of these interpretations? So feel free to plug in the values for either interpretation. Knowing weight gets you 36% of the way to understanding the variation in height. Exactly, exactly. And double check with your teacher on how they want you to interpret it. But that's what it means is like if you knew this X variable, then you would be this far to understanding the variation in the other variable. Or blank percent, so it'd be 36.13% of the variation in somebody's height is explained by the variation in their weight. This is one I generally use in 201. This is more over the 320, but basically saying, someone's weight's pretty important in determining their height. What you could do is you could add in another variable. We could do gender. Watch this. So now we get an R squared of 56% or 57%. So now the model, we could just say the model, and we could see what it looks like. We got two separate lines. So the model right here explains 57% or 56.8% of the variation in somebody's height. Like knowing somebody's weight and gender would get you 56.8% of the variation, would get you 56.8% of the way to understanding the variation in their height. Let's look at the interaction on here too. Oh, the interaction didn't do anything really, because the interaction is not statistically significant. But does that make sense right here? I'm just adding more things to the model, which all you have to do is do a plus or multiply for interactions. And you could look at multiple regression right here, which you probably haven't covered, so don't worry about that. But the interpretation still holds right here that 56.8% of the variation in someone's height is explained by the variation in their weight and gender right there. So very important to know what you're seeing and what the output means, because that's going to be key to interpreting it. What else are you wondering about, Olivia, right here? And let's see, 201's probably... We don't have any 201 here right now. My R squared is 98. So that means 98% of the variation. That is correct. And probably carry the next decimal usually. 98, whatever this says, like 98.2. Or it might be exactly 98. But 98% of the variation, or, yeah, and double check, like, maybe say to your instructor, does this look good? Because sometimes people are particular, especially if they teach a certain way. But interpretations are, there's a lot of ways to say things. But we want to make sure you can understand what it means. So hence, I always go and think about the theory first. Like, what are we talking about theoretically? It's actually the percent of variation explained from our X variable right here and how much it gets us to understanding Y. Where here where did our R squared of 100% go? Here's our R squared of 100%, where knowing the X variable would get you 100% to understand the variation in Y. At least for this data, we could say. So for this data, knowing X gets you 100% of the way to understand the variation in Y. This is indicator regression right here, where we have a categorical X But we do a trick to the categorical X where we make it indicators, which are zeros and ones. So technically, it's still quantitative. You say, wait a minute, gender is categorical. And I say, well, we could just do, we could do zeros and ones for it. But you say, well, wait a minute, Brian, what if you have multiple levels? Well, check it out. We would just do multiple indicators. We'll do handedness right here. So now we have multiple indicators for the different ones, and we can use 0 ones for the different lines. And that's not statistically significant. So if we looked at the drop 1 on it, all these are concepts you learn, and then we got to do test equals F. So all these right here are concepts you would learn in 320, knowing how to look at that output and say that handedness is not statistically significant. That means it does not bring new information to a model that already has weight included in it. It's probably not significant by itself, but if you wanted to do that, you'd have to just do a model right here and then look at, well, I guess we could do that then. Yep, it's not significant by itself. But it only tells us that it does not bring new information with a model where weight is already included, and that's the drop 1. And there's the sums of squared error reduction it gives. Only a reduction of 4 in the sums of squared error, where weight reduces the error by a lot. And this also. Fun fact, watch this. So you remember those quantities we calculated just a little while ago? If you go to the ANOVA and run it on the model, here is the amount of variation we explained. Here's the amount we didn't explain. So the total variation from the naive model would be what we explain and what we don't explain added up. And then here's what we explain. Oops. So here is what we explained right here. Here's the total variation right here. So remember that value? Oops. That value is the R squared. So the R squared is the amount of variation we explain, which is the reduction. And that value can be seen right here in an ANOVA table. And that was the value we calculated for how much was the difference between the naive and our model. So this is how much we don't explain with our model. We'd like that to be 0. And I can show that here theoretically. I'm just kind of rambling about theory because I love theory. So if you have a model that looks like this, we'll go 1 to 100, and then y equals 1 through 100, and m save into linear model, y tilde x, oh, capital X. And then we go right here and do an ANOVA. Well, the reason, there it is, like it, give a warning, right? Perfect fit. So the reason it's saying this is because we get a perfect model right here. And if you look, that means there's no error in the residuals. So if we were to look at the naive model right here, the naive model, I think I can plot that. So let's go plot of x comma y, I think it is. There we go. And then let's go AB line at the mean of y and col equals, where's my AB line? Am I still inside it? So col equals red and line width equals 2. Oh no. I thought AB line had that. The mean of y. Oh, h equals. There we go, there we go. And so that is the naive model right there. And you could look at our model too on here, AB line of M. There's our model. And let's start making this a little bit easier to see right here. Oof, it's going to look weird. Col equals blue. There's our model. And line width equals 2. So our model reduces all the error. And yeah, all that good stuff right there. That is the perfect model going through the data with the naive model as the red line. And the naive model is where we would calculate the original error of 83,325. Then our model has no error. So because of that, when we look at the summary of our model, we get an R squared of 1 right here. It's also telling us perfect fit because it's like, you sure you did this right? And then there's the equation right there. The intercept is basically 0. I hate that it does that. Yay! Yeah, these are the concepts. That's the naive model, which is always just the mean of y. And then our model right here is what goes through the data. So that's the y hats from the predictions. And we have explained all the variation in y. So 100% of the variation in y is explained by the variation in our x. We'll see if anyone else has any more questions. Might head off a little bit early today. We've got a big class today, big lab. But if you have questions, is there a playlist of your lecture videos? I can't put out the playlist, but you're always free to come by office hours. Thank you so much for asking. I appreciate that. It's like our department has a policy that whatever class you're in, then that's the class you're in. And basically, but a few people have asked, and I asked the department head to double check, and I really appreciate that, Olivia. But the department wouldn't want me like being like, everybody attend my class. Does that make sense? And then especially we have like asynchronous classes. So shout outs to anyone who's I double checked with the department before. Yeah, no worries. And thank you so much for asking. I'm throwing 100 points. You can tell teacher got like I got Brian's bonus points. But I had a person ask from the async, or I had someone ask, and then I double checked with the department head before replying, because I want to help as many students as we can, but then we also try to make sure, because imagine we want to make sure everything's fair across the board, because let's say some people have access to my lectures, some people don't. But then let's say you learn best from another teacher and you're like, oh, I'd like to go to so-and-so's class. Well, then they might have a lot more students, a lot less, and it would cause and then we might say, well, wait a minute, I taught it this way. So that's why I always say, like, check with your instructor. So you might have heard me say that a few times, like, oh, make sure this is the way they want you to interpret it. Like, I can tell you the way I would tell my graders to give you full credit, but I can't 100% promise, even though I go by these things right here. So to Alman, who's from a whole nother university, I can't promise the way I do things will be the way that your instructor will accept it. Your instructor could be like, no, this is not the way we do it. We do not interpret it that way. We say it causes this. If somebody gains weight, it'll cause them to get taller. And I'd be like, eee. We'll see if there's other people here. Whee! Feel free to ask more questions. What questions are there? I might grab some lunch. Busy day. Any other questions? Feel free to ask anything. Olivia, always feel free to swing by office hours. These are open office hours. Yeah, no worries. We'll see if anyone else swings by. I appreciate it, Olivia, and glad this helped give you a greater understanding. And thank you so much for asking. You're always free to ask things. You're always free to ask. We'll see. Let me look at Discord. The Discord. I don't see anything in the general Discord. Might have some messages. Here we go. Oh, wait. Oh, no. Got some message requests. Hey, Sam, can you go over Dataset for assignment 5? I found yesterday and had it on my computer only now, but I can't find the Dataset again. Yeah. Can you go over finding a dataset for assignment 5? Yeah, let's talk about that. Assignment 5 dataset. DS320 assignment dataset finding. It was along the lines of strength, height, and weight. Cool. What kind of topics are you interested in? What kind of topics are you interested in? So when you want to find a data set, you just go over here And so we need quantitative variables for this. So what kind of topics are you interested in? Sports. What's your favorite? 2 favorite sports, 3 favorite sports. So there's lots of sports data. You could actually use fast NFL or fast NBA or fast MLB. What kind of sports are you interested in? What kind of sports? Football? Here we go. What do you mean football? Let's type NFL. Because I guess it makes sense to call soccer football. Football statistics. This might be it. It's got height. No, this doesn't have enough. That's a really big file. I might not want to deal with that. Ooh. That one could work. Let's see. NFL Fast R. This probably has... No. Okay, this is good right here. So this data set has a lot of quantitative on it. We don't need all the other things. It's got different players, and it's got their passing yards, their passing attempts, and is it all the different players? So let's look what the data set says. The data set includes NFL offensive statistics for players from 2019 to 2022, passing yards, rushing yards, receiving yards. So it was inspired by my love of football and NFL right here. So this one right here would work right here. This is offensive stats for players. And you've got the passing interceptions, passing touchdowns, passing yards, passing attempts, passing completions. Might be for a game. Yeah, it's for a game ID. So it's for each game. So knowing the context is very important. This data set would work right here because what do you need for your analytics assignment this time? Ooh, and look, they're going to get some non-normality on this. Has there only been 5 passing touchdowns in a game? I thought there's games where someone gets like 6 or 7. You need 3 quantitative variables. 3 quantitative variables. Does that make sense, Sam, right there? Or Samuel? What about NFL combined data? Can you post that link in the chat? Oh, the combine, right? That's what it is. Might work. Oh, yeah, totally. This is an even better data set. I should have selected this one. Oh, this is great. Yeah. This is an amazing data set. So yeah, because we have a bunch of what's right here. This is great. Because we have a bunch of what's. I mean, you got a ton of these. Why is this such a great data set for this assignment? You've got a ton of these. And by a ton of these, I mean what's what you need for this week. You got a ton of them. This is an amazing data set. Ton of quantitative variables. So you're good and set on it. You just have position right here. Height, wait, this might be the one you found. All these different players right here and analysis. And it would be even better if you connected it to like their NFL career. So like you would then like merge a data set with their NFL career if they went to the NFL. And maybe then you could look at I mean, do you think an NFL team would find it important if you said, because you could try to do that. I could help you out if you wanted. That's more advanced, like going beyond this assignment. But if you don't do it for this assignment. Like this week, focus on doing just what we need. But I'd let you do it for the midterm probably. We're going to have a special thing for the midterm coming up. But you could take the data, combined it like with their statistics in the NFL and look at their NFL career compared to their combine and then see which combine statistics indicate the best abilities in the NFL. Like, does the combine really gauge? Because I know, like, someone would have to know what the combine is. I think that's when prospective NFL players go and get judged by their abilities. Like, they do the 40, they do different things right here, Is that right there, Samuel? Like the NFL players, before going into the NFL, before getting drafted, go to like a test your skill event, like show how good you are event. And so you can see there's kind of this ceiling, or we should say floor, on the 40 where 4.22 is absolutely insane. We'll probably know who that person is. Here, let's download the data set. This is a cool data set. So we're just going to download this and load this into R real quickly right here. This is a very good data set. And then I always want like not everyone to use it, because then I don't want everyone to be like, I'm going to use that data set because you found it. He's like, oh, this is a good data set. It is before the draft, exactly. So you need to download the data set, put the data set in your working directory, and then with the data set in your working directory, you can go to read.csv, and I renamed it Combine. And so we're going to call this Combine store into, and now we have the data. Does that make sense? Try getting the data right now. You want to download it, save it to your computer, put it to your working directory, and now I've got it loaded in. And you know what you can do now? It's easier to use here. You can just go right here and sort 40, and the person with the fastest 40 was Dante Stillworth. Those are the people. Chris Johnson, I know, did really well. He's done really well in the NFL. Marquise Goodwin, I think, too. Jacoby Ford. A lot of these people right here are people we've seen in the NFL throughout the years who are just complete amazing. I don't know why it's Josh Robinson one. I guess there's been multiple Josh Robinsons. But these things right here are qualities they look at for these individuals. Who's the tallest person who's been in the NFL lately? 7 feet. No, wait. Dennis. I thought I said Dennis Rodman for a second. Dennis Rowland, offensive tackle at 6'10". That is insane. And then they didn't have them do certain things. So if their NA is missing right here, that means that it wasn't done. Chapter 6 homework. Yeah, which one do you want to do, Mackenzie? Let me know which one you want to do. We can check that out. Who's the heaviest in the NFL? Mike Williams right there, heaviest in the NFL. And you can look at the positions. So what's really cool is you can just graph all this data and watch this. Is it GG Ally? Yes, it is this one. I would not show someone this graphic. Error. Oh, because player. Okay, so let's remove player. Oh, player has an error. Player has, oh, okay, strings as factors. Oof, this is going to look crazy here in a moment. Okay, strings as factors. How are you doing on this right here? Does this make sense on what I'm doing? Let me know if you have questions. We want to remove column 1 because position is more than 25 levels. Where was position at? Position -2. Or is it minus concatenate, I think? Because perf ID, where's that? There it is, right? Oh my gosh. What column is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I could just type perf ID in here. Can I do that? Well, let's do. Okay, warning. Oh, and it's telling me, wait, which column? Team. So that was 12, 13, 14, 15. And there's nothing else. Okay, cool. Which one do you want to do, Mackenzie, on chapter 6? Let me know. Oops. Wait, I thought I removed team. Oh, it's 14. It's going to look crazy here in a second. But let's see what it looks like. Suppose we were to collect data. You got it. I'm going to get that question up here in a second. Got it. And the graphic should be appearing. 50 warnings. Let's start the question here. Let me start loading in the background. And let me know if you have questions on this. It's going to make this graphic, I believe. I believe in it, but I would not put this graphic in a report. It's probably going to look pretty crazy. So we're going to get chapter 6 quiz going right here. While that graphic makes, that's going to take up all the memory in my computer. Suppose you were, so, and let me know what you're thinking about, Samuel, right here. This is a great question. Oh, we got it. Here we go. First one. We'll do this here in a moment as my computer gets slower. Whoa. What do you notice we have right here? Does anyone notice? It's hard to see. Man, can I make it smaller and you can actually see the text? Ah, oh, darn it. I want to like remake it one more time so you can see the text. This is a correlation matrix. This is a correlation matrix. And I should not have clicked that. There's a lot of statistically significant correlation. There's probably the psych package. Let me stop this from doing that. No, there's going to be a problem. What is it? The psych package library. Oh, do I not have library psych anymore? Oh, no. Or is it just mad at me? That's mad. It's really mad. Okay, so we gotta restart this. It's super mad. Okay, here we'll do Jacob. Samuel. Let me know if you want to come back to this right here, and we'll take a look. Mackenzie, good stuff right there. And yeah, okay, let's go over here and take a look at the 201 question. And here we go. Let's mark the time on this. Suppose you were to collect. Stat 201, chapter 6, quiz. Have you make sure everything's in your working directory, Samuel, right there. You might send me some pictures on Discord. Make sure everything's in your working directory, and then you should be able to load it. So you want to put all your files in your working directory. Make sure that's the name of the data. So it might be saying can't open connection. That means the file can't be found. So make sure to go and look at your files, which I can't get to anymore. It loaded in the bottom frame. Oh, but then make sure to store it. You want to store it up here. You want to save into something. So you want to save into something. So make sure to save the object into something right there. There we go. Make sure to save it. Okay, here we go. Suppose you were to collect data for each pair of variables. You want to make a scatter plot. Which variable? You're welcome, Samuel. Which variable would be best suited as the explanatory variable, and which would be the response variable? Why? What would you expect to see in the scatter plot? Discuss the likely direction, form, and strength for each of the parts A through D. Apples in weights, in grams, and weight in ounces. So both of these variables here are weight and weight. Which variable would be the best explanatory? Well, hey, Jesse, it wouldn't really matter which one we use because you're using weight to explain weight, and it's just different ways of doing weight. So either of them is fine because you're just trying to explain the weight in this unit, in the weight in this unit. So not a big deal. What would you expect to see in the scatter plot? Well, you're using weight to explain weight. So if you were to explain the weight of apples in one characteristic, it would actually be perfect because it's a conversion. You can just convert weight in grams to weight in whatever the other one was in pounds or ounces. It's just going to convert and be perfect. So the scatter plot would have a positive, straight, linear, strong correlation, and it would actually be perfect. For each week, ice cream cone sales and air conditioner sales. Oof. Okay, so the X is the explanatory variable. Probably ice cream sales. Truthfully, it could be either, so I'm a little bit mad at this. Let's see what it says. Either ice cream cone sales or air conditioner sales could be explanatory. Then the other variable would be the response, because ice cream cone sales can be predicted by air conditioner sales and air conditioner. That's kind of true right here. It depends on who we work for. Do we work for someone who wants to understand ice cream sales or wants to understand air conditioner sales? I would say either, and there is going to be a strong positive. We'll come back to that one. There's going to be a strong positive linear, and right here, it has to be positive. It's probably not going to be curved because the more ice cream sales there are, the more air conditioner sales there are. College freshmen, ooh, shoe size and grade point average. This is not my favorite question. There's a few questions on Pearson I'm not a big fan of. Hey, Andrew Wynn, good to see you here. So these would not have a relationship. I can just tell you that flat out, that there would really not be a relationship between someone's grade and their shoe size. Well, this one right here, if you think about somebody's shoe size, which they're probably just talking about numeric value of like 4 to like 20, and then their GPA over here from like 0 to 4, it's just going to look completely random. There's no relationship, and it would just look like that. So somebody's shoe size to their GPA, And probably people would want to understand their GPA. I'm not a big fan of the way they're doing this with the X and the Y, because usually the way when we have an X and a Y, we say this. This is the usual way we do it. Let's do a normal way of understanding X and Y. This is probably my least favorite Pearson question we've seen all semester. We will see the answers to it, so stay tuned. I just am not a fan of the way they're doing this. Imagine right here, I work for a restaurant. So we would go right here and pull up our tips data set. So in the tips data set, I work for a restaurant as a waiter. What is something I would probably want to understand as a waiter? What is something I would want to understand as a waiter? What is something I'd want to understand as a waiter? What is something I'd want to understand as a waiter, probably? My what's? The tip percentage, exactly. Great job, Cassidy, right there. So maybe it's how many people are in the party explains tip size, right? So what we could actually do right here is we could actually make a plot of this and look at the tip percentage we're getting. So this is our tip percentage. I think it is X and Y, so we're going to reverse this. See, it's up there, it tells me it's X and Y. This is not what we'll be doing into a 1, but we'd look at how many people are in the party. And, ooh, look at this. What do you kind of notice a little bit going on right here? It's weak, but I notice a kind of what relationship right here. A what relationship I'm kind of seeing. It's pretty weak, and there are some outliers, but I noticed a little bit of a what relationship right here. So what kind of relationship do you see in this data? I see it a little bit. I'm like, ooh, a little bit what right there. It's negative. It looks a little negative. So we can actually view it a lot quicker right here, and it's a little bit negative, as we said. And the correlation on it, we can just grab this right here and change this to core.test. And the correlation is this. And the correlation is statistically significant by the p-value. So this is a better way of doing these problems. The size of the party might explain the tip percentage we get. Larger parties generally tip a lower percentage. So you're getting your better tips from the 1, the 2, and then when you get to the 5 and 6 parties, they're giving you a lower tip percentage. Now, it might be because they're eating more, but they're tipping a lower percentage generally. So there's a negative correlation right here, and it's pretty weak because it's closer to 0. That's a much better way of asking these questions, to think about, you work at a restaurant, what would you care about understanding? The Y variable is the one you want to understand. So we'll do the other ones right here. Gasoline, number of miles you drive since filling up. So what? This is fine. This one's good. What would you want to understand if you're driving a car? What would you want to understand if you're driving a car? This one's obvious, I think. What would you want to understand if you're driving a car? What would you want to understand from that? You want to know your miles per gallon, but from this, it says the number of miles you've driven and the gallons remaining. So what would you want to understand? Would you want to understand how far you've driven or how much gallons are left in your car? Well, kind of how many miles you can drive, which is gallons remaining, right? So we'd want to know how many gallons we have remaining, which would be how many gallons are left in your tank, right? Exactly. So we want to understand, like, how much gas do I have left in my tank? And maybe how far we've driven will explain that. And that's how we know that. Like, it's like, well, how far have I driven on this tank? That might explain, that's kind of what our car is doing too. At least, I don't know how the gasoline thing measures it, but our car is kind of looking at how far we've driven and then kind of telling us, because that's the Y variable of interest. So this one is excellent right here, and it's definitely going to have a what relationship. So think the further you drive, the what the gas in your tank. This one's definitely a very strong what correlation right here. Like how far you drive related to how much gas is left in your tank is very clearly whatly related. The direction of it is very clearly whatly. And so I'll go ahead and answer these parts. Which variable, number of miles would be best? Driven and gasoline remaining would be the response, because we care about how much gasoline we have left, and it's very negative, exactly. So there is, the scar plot should have a negative, straight, linear, and moderate. No, it should be super strong. See, even here, it's going to be negative because the further you drive, let me double check, because no, it's not going to be curved. I mean, it's almost a 1 to, well, because sometimes you're driving on roads that you get better mileage on. I guess that's what they're getting at, is like, you can't be like, oh, I can only drive 5 more miles. What if you drive 5 more miles at 2 miles per hour? Well, then you're not going to drive 5 more miles. I mean, or maybe you will. I don't know how much gas you have left in your tank, but you'll need 2.5 gallons mathematically. So it's related to how fast you're driving too. So I guess it is moderate, strong. The other ones, which variable is the best right here? Which one was this? We probably want to understand grade point average. I mean, that makes more logical sense. We want to understand grade point average. So shoe size. See, I don't like that. That's very confusing. I would want to understand grade point average. But these are just not related. So they might be going for this right here for this one because they're not related. So just check my answer here in a moment. Either or on this one, it just depends. Are we selling ice cream cones? Or are we selling air conditioners? If we're selling air conditioners, then we'd want to know ice cream sales to understand the variation in air conditioners. So either one, then the other will be the response because ice cream, yeah. Okay, so I think we did everything. We might have got 100. I'm really worried about one or two of them. Oh, well, I'll be darned. That was one of the trickiest ones. That is one of the trickiest ones. I'm shocked we got 100. Because, like I said, in my reasoning for the air conditioner one was, well, what do we want to understand? But the problem is, you could go down to this one and say, what? Maybe we work for a what here? Think about how it could be technically either one, because maybe we work for a what? Maybe we're not a college freshman. Maybe we work for a what? You could be like, well, maybe I work for a this, so I'm more interested in this and understanding the variation in this, which would be your y variable of interest. Because then you could technically say either one. Like, that's where you're, like, thinking too much. I thought of it, like, as a college freshman. Oh, is that the context? You're a college freshman? Maybe it is. I guess you're a college freshman. You could say, maybe I work for a shoe store. So if you're like, if I work for a shoe store, then my y variable of interest would be someone's shoe size, because I want to know people's shoe sizes. And then grade point would be the explanatory variable. So just kind of key stuff right there, like what is the context of this, which is what we need for every problem. Very, very tricky question right there. But yeah, and once again, look at our example over here, which makes a lot more sense to say I work as a waiter. I want to understand my tip percentages. Maybe it's the party size that explains it. We could add other variables in here too, such as like the bill, and we would see larger bills. I wonder if larger bills, so there's larger bills have lower tip percentages. Yep. And we could do the correlation on this. It's going to be very negative. So there is a very strong negative correlation right here on this. So larger bills, lower tip percentage, kind of a bummer right there, right? That's when people order the extra thing. I actually noticed that in my restaurant. You'd get people ordering like really fancy wine and stuff. They'd be like, oh, I'll have the most expensive red wine you have. You're like, oh, darn. Like, they're not going to tip well. Like, I worked at Cheddar's. Sorry, Cheddar's. Cheddar's is a good place. But when you got people ordering really fancy stuff at a restaurant that's not too fancy, a lot of times then they're like, oh, man, wait a minute. My bill here is $80. It's just me sitting down. You're like, well, you had 3 glasses of the $18 wine. And, you know, your friend's going to come pick you up. 3 glasses is a good bit. I think we had a 3-drink limit. I think Cheddar's had that because there's something, I'm just going way off topic. There's the dram shop law in Tennessee. And the dram shop law is, which I do kind of stand by, not losing in personal opinions with Brian, is that, I don't know, everyone can have their own opinion on this. But if an establishment serves someone so much alcohol, chapter 6, the following data from, yeah, let's do that next. If someone serves so much alcohol to a person that they become intoxicated, that establishment can be legally held responsible for anything the person does to a certain extent. I mean, there's been instances, really bad ones, but I mean, it makes sense if somebody's at your establishment and I don't know. Now I think about it, it's like we should have a designated driver. You should call an Uber. Is it my fault? Like, you go to a liquor store and you buy a bottle of liquor. Can they not sell it to you if they're like, hey, we know you get drunk? I mean, like, I don't know. We're not going to fix society here today. We're not going to fix everything. So from continue to serve and serve. Yeah, exactly. Well, so the problem is then, because, you know, at what point? So it's right, Cassie. It's a tough question. It's like, how do we, I don't know. I waited tables a long time. Oh, here we go. We got the small data set. I kind of like waiting tables. It's kind of fun. Each table walks up. You know what I should do? I should go wait tables for a day. We should film a video like Brian waits tables for a day. Where would I wait tables at? Give your suggestions in the chat. Where would Brian go wait tables for a day? Just like relive the waiting tables and be like, hi, my name is Brian. Welcome to such and such. Yeah, everyone should wait tables for a day. You get some tables that are really nice to you would watch. You get, I don't know if I could film them. You get some tables that are really nice to you and just, you know, you got to walk up every table. This is the last thing I'll say on this. When you walk up to a table, you got to start figuring them out. You got to be like, do they want to talk? Do they want silent service? What do they want? And you walk up and you're like, hi, I'm Brian. And then they're like, hi. And you're like, okay, I'm not going to talk much to this person. You chapter 6 question about the federal. Yeah, how's it start? The Office of Federal Housing. We'll do that one here next. Thank you, Isabella. You got it. Got it marked. We'll do it here next. Every time you wait tables, it's a new experience. Okay, let's do this question here first. We got a few more, so let me focus and get this done. Considering the following data from a small bookstore, what do you notice about the data right here? As this goes up, the other variable does what? What do you notice about the data right here? As this goes up, the other variable does what? What do you notice? 5, 5, 7, 9, 10, 16, 16, 16, 17, 20, 15, 15, 17, 20, 20, 21, 23, 24, 25. It goes up. So that means they are whatly correlated. They are whatly correlated. They are whatly correlated here. Because as this goes up, the other one goes up. And they probably want to understand sales positively. So when you think, what would a bookstore care about? They would care about their sales. They're going to say, how much are we selling? Which they all have sales on the y-axis. This shows a negative correlation. This shows a weak or non-existent. It's pretty flat if you go through it. This shows a sharp positive. But if you notice, the number of salespeople is over here around 15 to start. This one starts around 5 and goes up to right around 20. So if you trace down right here, especially if you look at this, right here is where 20 is at, and that's the highest. And here's about 25. And you notice 20 and 25, that is the point. So it's definitely graphic A right there. What can you say about this? It's definitely positively associated. And what can you say about the form? The form means you have to draw through the relationship. And we generally go for how it generally looks. Generally looks. So if you draw through it and you get a general line, that's a bit of an outlier over there. I would say this is generally linearly correlated. So I'm going to be mad if they're like, no, it's curved. I'll be like, come on, come on. It's generally linearly correlated. What can you say about the strength of the linear association or the association? So strength is how tight it is around the form. Be careful though, because you can have correlation equal to 0 for a strong relationship. When is correlation equal to 0 for strong relationships? When is correlation equal to 0 for strong relationships? All of these relationships right here are strong. When is correlation equal to 0 for strong relationships? Correlation only measures one type of strength. Correlation is equal to 0 for strong relationships when? Correlation only measures one kind of strength. So when will we get a correlation equal to 0, but the relationship would be strong? A lot of people think this is always correlation equal to 0. That is correlation 0, but this other one in the middle has correlation 0, linear, exactly. There's no linear strength right here. That's super strong because the points are very tight around the form. Do remember, as we keep saying in 201, strength is tightness around the form. So let me ask you this. If we were to look over here at the following data, sure, and here is the equation, and let's go to our model. How strong is this relationship? Here we can go better. How strong is that relationship? Strong, weak, moderate, what do you think? And Cassidy, you're on the right. So careful. So how strong is that relationship, Cassidy? And I'll even show the correlation of it. The correlation of this is 0. It's super strong, and that's where, so the correlation is basically 0. That value right there is like so many ones. It's about like that right there. So the correlation is 0 because there's no linear strength. But strength is tightness around the form. This has a parabolic form. And how, as best as Brian can draw a parabola, how tight are those points around the parabola? How tight are those points around the parabola? They're super tight, right? So you would say that this has no linear strength. This has no, so it's super parabolic strong. It's very strong, as the notes point out right here. That relationship is very strong, but it has no linear strength. But there is the instance where it's just a non-existent relationship because the scatter right here is very wide. So you can have a lot of relationships like this. This is a sinusoidal relationship. Like over time, things go up and then go down. And there's a very strong, like, think of like seasonal patterns. Like if you work for a clothing store, you would say that there's a strong relationship between like time of year and sales, but that doesn't mean sales just constantly increase over years. It's like you have peak seasons, like you have seasons when you hit like a peak at the start of the season, people come and buy stuff, and then maybe it just like goes down again and then rises back up. And that's a sinusoidal relationship right there, like sine curve. So remember, strength is just how tight it is. This is very strong because the points are very tight around the line. Once again, if we were to draw the line, do remember we're only measuring linear strength of the line. The points, except for like that, there's a bit of an outlier. The points are pretty tight. So we say it's very strong. Yeah, it does. You better tell me I'm right. You better. Really, really, really ridiculous. 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 It's a mild outlier. I am literally going to do something right here. 2 seconds. This question made me very unhappy with that last thing. We are going to mathematically check Pearson because I can tell you for certain. That's why we get to the problems right here. Okay, so this is workers. L for my Pearson. Well, let's find out if they're right. Let's see. Let's find out for exact certainty, are they right, by statistical processes. So I can actually check this using statistical techniques. So this is a smaller data set, so I'm just inputting it all manually. Oh, did I get it all? There we go, 25. Is that right? And then make the linear model of sales explained by workers. Oh, I missed one. 15, 15, 17, 20, 20, 20, 21, 23. Is someone saying the 23 right there? Yeah, I want you to look at the scatter plot. And so here is, I'm just remaking their data over here in my software. Here's the model. And this is the point I thought was an outlier. It actually looks less like an outlier to me now. So maybe I agree with them. But here's how I can tell if it's an outlier. Is that point an outlier? The answer is it's not. That point is not an outlier. So we do not have, and yeah. So that point is not an outlier. I stand corrected. It's mild outlier. It's the point over here at right there. So it doesn't have that high of leverage either. So it's this point right. Yeah, my deleted studentized residual of -2. Little bit of an outlier. Not that big, but a little bit. And so that was the point I was most concerned about right there. That point deviating from it. And yeah, so does it have a curved relationship? I want to see that too. Did we have another question? I think that was the last one we have, right? The federal office housing. We'll do that one here. Does it have a curved relationship? Not really. No, Akaike says no. So it doesn't really have a curved relationship either. But at that point, yeah, it's a very small data set. So that last question is a little bit tricky right there. Once again, why we solve these in office hours. Two statisticians are going to disagree on it, but no one can disagree on the deleted studentized residual of it, which is a little outside of -2 for that point, which is pretty unusual on deleted studentized residuals. More on student T coming up in Stat 1 later, and residuals in Chapter 7. So we've covered some of these concepts earlier on. Residuals will be covered in 201. A deleted studentized residual is covered in 320. So Mackenzie, does that make sense right there? That's the first thing I got wrong today. No! And then I say to Mount Pearson, let's calculate all those numbers. It's not a highly influential point. So, okay, so it's not influential because it doesn't have enough leverage, but it is a bit of an outlier via deleted studentized residual of a quantity of outside -2, which think about your normal curve outside of 2 and -2 is mild outliers. So deleted studentized residuals, studentized just means turn to t-scores. Yeah, awesome, Mackenzie. Yeah, glad you can make it here too. Sometimes I go into a little bit higher of details, especially if we get a little something wrong on my Pearson. have a question about the exam. We'll be able to use the stats app. Nope, you won't use the stats app, but you will solve questions. Check out class yesterday. So if you're in our sections, we did a lot of problems where we wrote down example problems right here, where you'll see pictures like this. So check out the end of class yesterday where we covered multiple versions of what you would do on the exam, where you might see pictures of the applet, maybe the David M. Lane applet, or this applet right here. But knowing how to read the applet is going to be key. I think we have one more question on the docket for today. The Office of Federal Housing. The Office of Federal Housing. I did like that question until it threw us for a curve at the end. It's like, is that an outlier? I guess, you know what I think they try to go for? I think they try to go for obvious outliers, things that are like very big outliers. So that wasn't a big outlier. It was a mild outlier. And that's the problem. If you start to look at things too much, you'll be like, well, that's kind of an outlier. And so in statistics, we usually go for the more obvious ones. We say, oh, yeah, that's a big outlier. So like there's no real outliers in those. The fastest horse. So always think about, we will especially do that on the test. We'll go for the more obvious questions. We won't give you one that's like, is that an outlier? I should use that reasoning that my Pearson wouldn't give me a iffy one, because it is just basically -2, which is kind of iffy, Oh my gosh. Where's that question? Did I skip it? Ah, here it is. So what do we see right here? Strength, direction, form, unusual features. Well, we got to mark the timestamp on this so people can come back and check this out later. Get it all right. 1:52, 53, start 201, chapter 6 quiz. Okay. So with this one right here, the correlation is 0.64, which is moderate strong. Moderate's about 0.5. Sign doesn't matter if it's negative. It's just negative direction. Still about moderate if it's negative 0.5. Strong is about 0.75. And I say about because these are just subjective words. So it's between moderate and strong. So moderately strong. More on that as we look at the answers below. And I don't really see any big outliers. I do see what is called heteroscedasticity. That is called plot thickening, which we cover more in chapter 7. And that's a little bit of a change in strength. I don't think they're going to go into that much detail on it, but you can see it's stronger at the bottom because it's tighter. We talked about that in the previous question, that the tighter it is around the form, this is a linear form right here, the stronger it is. So it's much stronger down here at the bottom, and it gets a little bit weaker over here at the top. That's more of a chapter 7 topic with plot thickening, which the technical term for it is heteroscedastic. We want what is called homoscedastic, same thickness throughout. So little bit of an issue on this plot, but mostly a positive relationship, and actually gets stronger over here, but that's a lack of data too, so we don't want to make too many assumptions at the end where there's very little data. But, you know, it's a good regression, or good correlation, because we usually don't see things this good when we look at data. Sometimes it looks pretty random and outliers and things controlling it. So there's not really any big issues with this. Looks generally good. There is a moderate positive. You see it says, but it's not linear. So I wouldn't pick strong. I'd go with moderate positive because it goes up, it's positive, and it's linear. If both variables were standardized, what would happen to the correlation? So this actually goes to the equation we use for correlation. And when you look at the equation for correlation, the equation actually uses z-scores. Since the equation uses z-scores, well, nothing would happen. Nothing at all. Jesse knows right there, well, if you standardize it, well, we already do standardize it. So the correlation would remain exactly the same right there. If median family income had been measured in thousands of dollars, the correlation would have the same sign. It would not change it, and the magnitude would not change. Suppose Washington, D.C. is added to it, and it's 548 and 45,000. So let's go right here and add that to the plot. It is 548 and 45,000. So when you look at that point right there, I think it's 548 and 45,000. That's what it said it would be, 548 and 45,000. Yep, that looks to be where it's at. How would that change the correlation? So points towards the center are going to make it stronger. Points towards the outside are going to make it weaker. So that point is way on the outside. It's not going to change the sign of it because the line's still going to go up. We could, unless you put a point way, way, way over there, which they're not going to try to do, because that at some point that point could maybe, if it's way off the curve, way off the chart. But this is going to make it weaker because it's not towards the strengthening part of it, which is along the linear relationship. So overall, this will make it weaker because it's towards the outside, and that's going to expand kind of the central area of the points, making the spread of it further apart. Because remember, strength is how tightly clustered the points are around the form. So those points are not as tightly clustered. The signs would not change. It would have the same sign, but the magnitude would decrease. It wouldn't be as strong as a correlation. Do these data provide proof? No, we never say it. These data do not provide proof since the value of correlation coefficient cannot prove any causation. So yes, really good question right there. That covers a lot of key concepts about like what can outliers do, and adding in the outlier also goes a little bit over the kind of standardization of values right here. That's not going to do anything to correlation. And so we should know where to look at in the notes. It's hard to like, when you think about questions, you know, you don't want to be like, write the equation for correlation, because that's not learning anything. But what does this equation tell us? Well, correlation is using z-scores right here, which are unitless. So if you were to change the units of the problem, it wouldn't change the correlation because you would still have the same standardized units. That's what it's saying right here. If you were to standardize them, well, you're already doing that. So Jesse and everyone, good work. I think that's got it. Until then, we'll be doing class here for 320 just a little bit. Bye for now, everyone. Bye.